Welcome to the lecture of analysis of several variable, and this is the second lecture of the model for partial derivative and directional derivative. We will continue with the 4.1 section 1 of model 4, which is partial derivative of several variable functions, and we are going to state and prove one theorem. Let omega be open in Rn and A is a point in the omega, and we have a function f is from omega to Rm, and we assume that this is a differentiable function at A. Then all the partial derivative of f at the point A exist. Means you have here, as it is from Rn, so we have n variable, so f has an n variable, so x1, x2 and xn, we are denoting those variables. So therefore the function f is partially differentiable with respect to each variable at the point A. And further we have the partial derivative with respect to a particular variable k. So xk, we will have f dash a e k. So while ek is the unit vector 0 0 1 0 0. So this is the kth entry, and the for all h belongs to Rn, we can write this is as f dash ah can be written as the partial derivative with respect to x1 h1, with respect to x2 multiply h2, and with respect to xn multiply hn, and which can be formulated by this summation. So now we are going to prove this theorem. Since the function is differentiable at A, from the definition of differentiability, there exists R greater than 0 such that f of A plus h is equal f A, f dash ah plus absolute value of h, epsilon h for all h belongs to B0 R, where f dash A is linear from Rn to Rm, and epsilon h tends to 0 as h tends to 0. Now for k equal 1 to n, we have del f del k is equal limit t tends to 0 f a plus t e k minus f a t. So this is from the definitions of the differentiability of a function, and we have that this f dash a is linear from Rn to Rm, and this epsilon h will goes to 0 when absolute value of h tends to 0. Now we already formulated previous lecture that partial derivative with respect to a variable xk can be written in this form. So we are going to use this to prove our theorem. So this formula is given in the previous lecture, slide number 6. Now this del f del xk, this is limit t tends to 0 f a plus t e k minus f a over t. So from the previous formula, this formula, we open it now. This we open it, and then we got it. This formula f a f dash a t e k plus epsilon t e k epsilon t e k minus f a over t. So this fa and fa will cancel out. Then we will have here limit t tends to 0 t f dash a k over t plus limit t tends to 0 t e k epsilon t e k over t. So this terms we separate it. Okay, so now we'll see that how the limit will look like. So now from where this part is coming, t f dash a e k. So from here, how we can convert this is as t f dash a e k over t. So what we have, f dash a is linear from Rn to Rn. So therefore f dash a t e k. So this t can be taken out. So you will get it here t f dash a and operating on e k. So this is written from this ideology. Okay, so this t and t will cancel out, and then we have to try to check this, what is the limit. So to calculate the limit, we'll have here consider two cases. First, consider t is greater than 0. So therefore, absolute value of t e k over t will goes to t absolute value of e k epsilon t e k over t. So now this t cancel out. Then we will have absolute value of e k epsilon t e k. Absolute value of ek, this will be actually 1, but we leave it here as absolute value ek, and this epsilon tek will tends to 0 as we shown with the conditions of the differentiability. So therefore this whole limit is going to 0. Now next we have here when t tends to 0 minus again, so absolute value of t will be minus t. So this t and t cancel out, and we will have minus, and then with the same logic as previous, this will be 0. So therefore, overall, the limit is 0. And we'll have the partial derivative is f dash a, which is the part a. So therefore, partial derivative exists for all k is equal 1 to n. For the part B, let's for any h belongs to Rn, we have h is equal h1 is to hn. So this is h1, we can write it h1 1 dot dot 0 and then hn 0 1. So therefore this one is actually e1, this is en. So we can write it like this, h1 e1 plus hn en. So this can be written as k equal 1 to n hk ek. So this form of h we are going to help to prove our theorem. So now the last part is that f dash a h. So this can be written as f dash a h is replaced by this form as proved in the previous slide. Now f is linear, so therefore we can move it inside. Sorry, f dash a is linear, so we can move it inside it, and hk can be taken out, so we can combine this part. Now f dash a ek from the first part can be written as the partial derivative with respect to x. So this proves the theorem. Now we have an example here. Let f r2 to r defined by fx is equal x y x square plus y square 0 and xy is not equal 0 0 and 0 when xy is equal 0 0. So now the question is here, find del f del x 0 0 del f del y 0 0. Second is f is continuous at 0 0, and third is f is differentiable at 0 0. So we are going to answer this question. So first we'll calculate f del x. So part A here, del f del x. This is, we can do two way. So it can be like this, del f x0, and at the point x is equal 0. But this is at x0, the function is still 0, so therefore the partial derivative will be 0. So this is one method, and another method, method 2, we can do like this, del f del x is equal limit h tends to 0, f of is 0 minus f of 0 0 over h. So this case also, limit h tends to 0, 0 minus 0 over h is equal 0. So same way, the del f del y at 0 0 is at 0 0. So this is equal del y f 0 y at the point y is equal 0. But f 0 y is 0, so therefore we will get the derivative is 0. So therefore both partial derivative of f at 0 0 exist. Now part B, to show the continuity, let one sequence an is equal 1 over n, 1 over n. Then limit n tends to infinity an is equal 0, 0. But f of 1 over n, 1 over n, this is equal xy. So it is 1 over n, 1 over n over 1 over n square plus 1 over n square. Here we will recall the function f of xy is equal xy over x square plus y square. So this is equal 1 over n square over 2 over n square is equal half. So therefore an tends to 0 as n tends to infinity, but f of an does not tends to f of 0. So therefore f is not continuous. Now part C, since f is not continuous, it cannot be differentiable at at a is equal 0 0. Now remark, in this example it shows that partial derivative does not depends on the continuity of the as here the partial derivative of 0 0 exists though the function is not continuous. Our next lecture is on Jacobian matrix involving several variable function, and that will be the section 4.1.